Let's continue right along. What is this showing? This is showing the things, lots of things on Earth rotate, including the Earth, right? Okay, so actually what I want to do is start with this observational experiment. Then we'll get to the thing that just went on your screen. So this is the basic idea, is that if you push on a wheel, like it's happening right now, it's sitting here stationary, you push on it, doesn't move. If you give it a little bit of a force upwards, then it starts to speed up more and more and more until you stop giving a force, in which case it just spins around at a constant rate. And then you have to push a force down the opposite direction to slow it down. So the way that it kind of goes through that is, first of all, observational experiment number 1. Since this force is along a line which connects to the rotation axis, this is 0 torque. And so it sort of makes sense that there's 0 motion. Or 0, actually, to be more accurate, there's 0 angular acceleration, as it turns out. That's going to come back later. But certainly it's not moving. So the next experiment is when I started trying to rotate it. So I apply a constant force. I push lightly and continuously on the outside of the tire. And these little dots are showing a motion diagram. T0, T1, T2, T3, T4, and T5. And the interval of time between any of those two adjacent dots is the same. Like there could be seconds, ticking off the seconds. So what that means is that it starts off moving slowly, and then it speeds up more and more and more and more. So this is actually counterclockwise. So what kind of, is that positive or negative? Positive, I think, torque. Torque, because here you have now this thing R, and this force, the torque is going to be equal to F times R times sine of 90 degrees is the angle between the force and the R vector. And so, and sine of 90 degrees is equal to 1, so just F times R. And this has got positive alpha. Positive angular acceleration alpha. Not only has it got omega, it's moving, it's also omega is continuously increasing, getting faster, faster, and faster, and faster as it spins, as it's spinning. Then you let go, 0 torque, you release the spinning tire and watch it, and look at those T5, T6, T7, T8, T9. Those are all equally spaced. So what this is it's 0 torque, because you're no longer forcing it. And I guess we've neglecting friction here. Friction is somehow negligible for this little demonstration. Omega is constant, and so the rate of change of omega, this alpha, is 0. So moral of the story is 0 torque, 0 alpha. This is a case where it is moving, but it's moving in a uniform circular motion. So it's not speeding up, not slowing down. So the angular acceleration, and I guess this tangential acceleration, these are all 0. Make sense? And then the last experiment is that you slow it down. So you're now applying a force. If this is R and this is theta again, you got torque is equal to negative F times R. This is a negative torque. If you look at those, the numbers on the T's, it starts off at T9, T10, T11, T12, T13. So it's actually still rotating counterclockwise. Omega is still positive, but it's decreasing. So what does that mean again? If it's slowing down and omega is positive, that means that alpha is negative. So omega is positive. It's slowing down, so that means that alpha and omega have opposite signs. Slowing down, sorry, not slowing downs. So alpha is negative. Negative. Same as the torque sign. So what we're all trying to get at here is this idea that we think that torque is proportional to angular acceleration, or say alpha is proportional to torque. If something has some angular acceleration, then it must be experiencing some external torque. And that leads us to this question, which I hope you still see, actually, on your phone. But here's a diagram for it. You've got a car, and it's accelerating towards the right. So, which way are the wheels turning? Can you imagine? It must be going this way. Clockwise, I guess. So the reason the front wheels, which are connected to the engine, the reason those are turning is because you stepped on the gas and there is some internal engine torque on those front wheels. So, but anyway, the question is, as you accelerate, what is the direction of the force of static friction of the road upon the front wheels? Give me a minute to think about that. And by forward, I mean like that way, to the right, or backwards is to the left. Okay, so whoever answered A, I think is good. So the way it goes is that, the way I like to think about static friction is that I think if it wasn't there, some surface would be slipping. And so which way does that static friction have to act to prevent the slipping? So this tire, if it was just a little up off the ground or something, and you, I don't know, maybe the whole car was lifted off the ground and you went like that, and you dropped it onto the ground, to prevent that slipping, there'd have to be a forward force of friction on the tire because it wants to slip backwards. Does that make sense? You go, and then I guess you're pushing backwards on the road, the tire is pushing backwards on the road, so the road pushes forward on the tire. And it's actually a huge force, and it's what gets your car going. Okay. This is part 1 of 2. Part 2 of 2 is what about the back wheels? Well, this is not an all-wheel drive. This is a front-wheel drive car, which most cars are, unless it says AWD and it's a Subaru or something. Then your engine is actually only just connected to the front wheels. So what you need to think about when you watch a car go is, do the back wheels also turn? I think they do, right? Like every kid who's looked at a car, they see all four. It says front wheel drive, but all the wheels are turning. So how does that work? Is there, I think if something turns, there has to be a torque on it, I guess. But it's not coming from the engine. So think about that. I'll give you a minute. Well, okay, so here's what I think. This one is a little more controversial. So what I think is happening here, again, so because it's front wheel drive and because the front wheels are connected, the whole car is accelerating towards the right. That's a given. Okay? The question is, what's going to happen to those back wheels? Well, if they weren't touching the ground, they wouldn't rotate at all because they're free wheels. So they do rotate, and that's because they're getting dragged along. Want to do that again? If it was slipping, if it was somehow frictionless back wheels, they wouldn't turn. They would just sort of slide along like that. But they do turn because there's a backwards force of static friction on the back wheels. It's not very much. All it needs to be is just enough to rotate the back wheels. It's a small static friction backwards force. But it's still there. So what I would the way I draw it on my screen here, if I can find my pen, as I would say, there's some giant forward force on the front wheel, and there's some little teeny force here, which is just rotating them like that. Another way of looking at it, why does the front wheel rotate? Because there's a torque from the engine. Why does the back wheel rotate? Because there's the torque from static friction. Okay. Any questions about that one? It was a tricky one. Okay, so, all right. You got a rigid body. It has some rotational inertia about some axis. You have some torques coming from various forces, and they produce a net torque. If that happens, so I think what we've done before in static equilibrium problems is that we've actually set the net torque to be 0. That's sort of equilibrium. Now we're going a step further and we're saying, well, what if the net torque is not 0? Then the thing has angular acceleration. And the angular acceleration of the object is given by the net torque, all the sums of torques. They're going to end up being clockwise or counterclockwise, depending on how they all are balanced. And then you divide it by the rotational inertia. And somehow the units all work out if you use SI. So this is back to that analogy chart that I had. Down at the bottom, so it's the same way that you got acceleration is F net divided by mass. Now you have angular acceleration is torque net divided by rotational inertia. Let's do an example. The engine of a small airplane is specified to have a torque of 60 Newton meters. Upon, I guess it's must be on some sort of propeller or something. So there's the propeller. The torque of the engine is equal to, we'll call it plus 60 newtons times meters. And this propeller, the engine drives a propeller whose rotational inertia, I, is equal to 13.3 kilograms times meters squared. On startup, how long does it take the propeller to reach 200 RPM? So I think that's saying that omega final is equal to 200 revolutions per minute. That's what the RPM stands for. So I'm going to write it down like that. And it's saying how long does, so that means find t. And I think we're going to assume that the propeller starts at rest. So omega 0 equals 0. Otherwise we can't do this. So we're going to use Newton's second law for rotation. Which is just that alpha is equal to the torque divided by I. And then we're going to use kinematics. So we're going to go back to that aid sheet, which I've already put away. But what do we have? We have omega final seems to be important now. And also we've got alpha, and also we've got omega. So I think the one that I'm going to use, let's use omega is equal to omega 0 plus alpha times t. I think that's going to be the easiest one. And omega 0 is equal to 0. And we just solve for t. So you get t is equal to omega, I'm going to call this omega final, because that's what we called it up here. Omega final divided by alpha. And we're going to take alpha from Newton's second law for rotation and plug it in. So put it down here. So the time is equal to omega final. And you divide by I, and you get torque. The thing that's the problem here is this revolutions per minute. We're going to have to convert that to SI units because we've got here I is in kilograms meters squared. That's a SI unit. Tau is in newtons times meter. Those are all SI units. The RPM is not going to work. You're going to get totally the wrong answer. So let's convert omega final to SI units. I'm just going to do that sort of separately here. I got omega final is equal to 200 rev divided by minutes. So I'm going to times it by two things. Something that converts revs to the SI unit for angle, which is what? Angle? Radians, yeah. So we want radians on the top, and I want revs on the bottom so that the revs will cancel. Do you know how many radians are in a whole revolution? 2 pi, yeah. So that's something you should know. So that will take care of this rev thing. And then minutes is not the SI unit of time. What's the SI unit of time? Seconds. So we want seconds on the bottom and minutes up here. So there's 60 seconds per 1 minute. That way the minute will cancel minute. So I get 200 times 2 times pi divided by 60 is equal to 20.94 radians per second. Running out of room here. So I got T is equal to 20.94 times 13.3 divided by 60, which was the torque. And I got 4.64. I guess it's probably seconds, right? Because it's SI units. And I think that's what I want to do. So Brian said I can just do a units check and evaluate if I want to. So I don't know, 4.6 seconds might be okay. Let's do a units check. He said that's worth 2 points. So let's check units. So what I think is we're going to check the units of time. So time was equal to omega final times I divided by tau. So the T units are going to be equal to omega final units, which is radians per second, times the I units, that was kilograms times meters squared, divided by the tau units, and that was newtons times meters. So I guess the meters squared cancels this meter. You get the T units just equals radians times kilograms times meters divided by newtons. Oh, then there's a second from the radians per second. Somehow that's going to be seconds. Oh yeah, so there's newtons down here. So what's a newton? So remember that F equals ma. So a newton is equal to a kilogram times a meter per second squared. So let's take that and plug it into here. So T units is equal to radians times kilograms times meters divided by seconds divided by kilograms, meters, and then per second squared. And so now kilogram cancels, meters cancels, this second cancels, this second cancels, and you get T units is equal to radians times seconds. Oh yeah, and then seconds is, the radians is a magical unit, so you just cross it out. And then you say, like, yeah. So I guess units are okay. That's my evaluate step right there. So that's just using Newton's second law of rotation. And also we had to combine it with some of the kinematic stuff. Okay. So the next thing that comes up a lot is these constraints of rolling without slipping. And it comes up sometimes in Pulley questions. So this is what I want to go on to next. Massive pulleys. A real pulley has some rotational inertia. You can imagine a frictionless surface up here, a mass m2, a pulley, and a mass m1. The whole thing's going to accelerate, right? This is going to go down. But in real life, the pulley will actually turn. The rope will move with the pulley. It'll stick on the pulley, and then you need, I guess, some torque if it's going to have angular acceleration. Makes sense? So where does that torque come from? What external force could cause the pulley to rotate? What's the object causing the pulley to rotate? That's a string, I think someone said so. So the string has to provide some torque on the pulley, and that comes from the tension in the string. The way I like to think of it is that you've got this taut string. It's kind of pulling inwards on anything that it's attached to. So it pulls to the right on M2, it pulls upwards on M1, we kind of know that. If you just look at the pulley as being your object, this tension up here on the left is pulling it to the left. So that's a kind of a clockwise or counterclockwise torque from that tension. This tension is pulling it down. So that's a clockwise torque. Those are pulling in opposite directions. And so if it's going to accelerate, now the tensions in these ropes cannot be the same. The tension changes as it goes over the pulley because it has to angularly accelerate the pulley. There has to be a net torque. So I'm going to kind of go a little backwards in time for a minute. This is a question that should be review. It's not a Chapter 9 question. This is an old question. I'm going to read it, and then I'll give you a minute to think about it. Mass M2 is on a frictionless table. It is attached to a cord that wraps around a massive pulley, and it is attached to a hanging mass M1. Let's just think about M1 for a minute. After the system is released, how does the magnitude of the tension in the rope attached to M1 compare to the magnitude of the force of gravity on M1, M1 times G? This should be in your memory banks from earlier in the course. Yeah, so someone asked, is M1 greater than M2? It turns out we're going to do an example where M1's less than M2, but in any case, it's frictionless up here. So the net force, I guess the net force in M2 is just going to be towards the right. That's it. It's just the tension, because the normal will cancel the gravity, and so certainly M2 is going to accelerate towards the right, which means this thing's going to accelerate this way, which means that this M2 is going to accelerate, or say M1 is going to accelerate downwards, right? So if you do a force diagram on M1, you've got M1G down, you've got tension up, you've got acceleration is going to be down, so F net, I guess down or something like that, is going to be M1G minus T1. It's got to be greater than 0. You have to have more gravity pulling it down than tension pulling it up, or it won't accelerate downwards. You can't have a balance. You can't balance these forces. So when M1G is greater than T1, that's B. Follow me? Okay, now we're going to apply that same kind of reasoning to angular acceleration of the pulley. And this is harder. This is a Chapter 9 question. How does the tension in the lower rope compare to the tension in the upper rope? Both of which are exerting torques on the pulley. Is your hint? I'll give you a minute. Okay, so it's not at all obvious, but what I would do, this one is accelerating to the right, this one is accelerating down, so that means that this pulley has got angular acceleration that's kind of clockwise like that. So if I do a force diagram of the pulley, well, it's going to look like this. There's going to be some force on the axis. I don't know what it is, doesn't matter. Then there's going to be this leftward force of torque, of tension 2. And then there's going to be this downward force of tension 1. And so I would say that T1 times R has to be greater than T2 times R for a clockwise torque, net torque. Whatever force there is on the axle is on the rotation axis. That's what's holding the pulley there. Doesn't matter for torque. The torque is coming from the string. So I think it's got to be A. Any questions about that? It's the concept. Yep.
So for like this question, the clockwise is the positive?
Yeah, no, well, yeah, you can do it that way. It's historical, but I mean, the other way of looking at it is that if you define counterclockwise to be positive, then this is a negative alpha, so you need a negative torque. And in the same case, this is the one that provides the positive torque, this provides a negative torque, so the magnitude of T1's got to be greater than the magnitude of T2. Okay? You can define your convention either way. I think for this problem it's actually a little easier to define clockwise as being positive. But okay, so basic idea. When an object is attached to a pulley, the distance the object travels is equal to the change in the angular position of the pulley times its radius. Okay, because the rope doesn't slip as it goes over the pulley. That's S equals theta times R, where R is the radius of the pulley and S is the distance either one of these travels. It could be X or Y here. If you take the slope of S versus time, you're going to get the thing that the velocity of either of these masses is equal to the angular velocity of the pulley times R. And you take the slope of this V versus time graph, you're going to get that the acceleration of either of these objects is equal to the angular acceleration of the pulley times R. And that's the key equation that you're often missing in these kinds of problems. So this is a useful equation. I call it the massive pulley constraint for problem solving. And I'm going to give you an example of that right now. Now I've given actual numbers to the masses. M2 is 2.5 kilograms, N1 is 0.75 kilograms, so that answers your question about which one's more massive. M1 is less massive. This thing accelerates towards the right. There's your T2 up here, and here's your T1 there, and this one accelerates downwards. So I'm going to, the question is, after the system is released, what is the acceleration of M1 as it falls? And it's a massive pulley, and it gives you the rotational inertia of the pulley and the radius of the pulley. We're going to assume no friction in the axle of the pulley, meaning that it's sort of a frictionless pulley there. So the net torque on the pulley is from the T1 minus the T2, something like that. So what I'm going to do is draw 3 force diagrams because there's 3 objects. I'm going to draw one for the M2, the M1, and the pulley. Okay. Each force diagram is then going to give me a Newton's second law, and there'll be 3 equations, and I can solve 3 unknowns. And that's how you do this. And the tensions are going to be unknowns, and the accelerations. So the M2 diagram just is, well, you've got the normal force, and then M2G, those cancel. So really you just got T2. And so you just say that the sum of the forces, I guess in the x direction or something, is T2, which is equal to M2 times A. That's that one. It's relating to the unknowns T2 and A. And then the M1 diagram, it's hanging, so you just got T1 going up, and you got M1G going down. Now I'm going to define plus is down here. So the sum of the forces on this is going to be m1g minus t1 is equal to m1 times a. And it's the same acceleration. And now I'm kind of running out of room for my pulley, but you got it, right? You've got this pulley. It's a circle. The two important torques on it are coming from T2, which is at a right angle to this R. And the other one in the opposite direction is T1, which again is at right angles to R. And then no torque from the axle. Here I'm going to define plus is clockwise. So what I get here is, still on this, the sum of the torques is equal to T1 is the positive one times R times sine of 90 degrees minus T2 is the negative one, and this times sine of 90 degrees. And that's going to be equal to I times alpha. So it's an easier way of putting that. These sine 90s are 1, so it's T1R minus T2R is equal to I times alpha. So 3 equations. How many unknowns do we have actually? So put that over here. The unknowns are actually T1, T2, A, and also alpha. So actually we have 4 unknowns and 3 equations. We've got M2 times A is equal to T2. This is equation 1. We've got M1 times A equals M1G minus T1. This is like equation 2. We've got I times alpha is equal to T1R minus T2R. This is equation 3. We need a 4th equation. Can anybody think of one? We're dead. Forget it. No. It was on a previous slide. Yep.
A is equal to alpha times R.
That's it. So this is that constraint. It was the rolling without slipping constraint, and it's also the massive pulley constraint. It was on a previous slide, so that's a good call. We need it. So its acceleration is equal to alpha times R, and that's it. Now we've got 4 equations, 4 unknowns. Yeah, ha, ha, ha. This is what I call the pulley constraint. It means that the rope is not slipping when it goes over the pulley. It's kind of pulling the pulley along with it, right? So that's important. If it doesn't do that, we can't do this. Okay, so now we have 4 equations, 4 unknowns, and that's it. We've done all the physics. We just have to do the math. Solve for A and eliminate all the other unknowns. Ready? Okay, it's just some algebra now. You guys can do this. I think that we're going to eliminate these things. So 1 implies that T2 is equal to M2 times A. Equation 2 implies that T1 is equal to M1G minus M1A. And if you combine equations 3 and equations 4, I get that I times A divided by R is equal to R times T1 minus T2. And we have T1 and T2 up here. So we're going to plug these in. It's going to get a little messy, but we're okay. I times A divided by R squared, because I'm pulling down this R now, is equal to M1 times G minus M1 times A minus M2 times A. So A, I'm going to pull out this factor of A. Everything with an A in it, I'm going to bring it over to the left-hand side of the equation and pull out a factor of A. There's an A times I over R squared plus an M1 plus an M2. And then anything without an A in it, I'm going to put it on the right-hand side of the equation. The only thing that doesn't have an A in it is M1 times G. And now I've solved it. So A is equal to M1 times G divided by I over R squared plus M1 plus M2. And I can plug in numbers for that. But before I plug in numbers, I just want to admire the beauty of this equation. I mean, just look at this thing. You know what the acceleration is? The sum of the forces divided by the mass usually, right? But here, there's only one real force that's driving this pulley. It's the gravity on this M1, M1G. That's your external kind of driving force. And here it is on the numerator of this equation. That's the kind of oomph that's pulling it. What's resisting it? Well, it's not just pulling itself, it's dragging these three things with it. And each thing has its own inertia on the bottom. You've got the sum of kind of like the masses on the bottom, except you had to convert this to kilograms, so you had to divide by r squared. Kilograms plus kilograms per kilograms. These are all the three things that are getting dragged along by this. I mean, it could not be more elegant. Did you have a question? Yes?
Does that mean that for all questions now involving pulleys, we assume that the tensions are...
Yeah, unless it says a massless pulley, then yeah, you have to assume that the pulley's got some mass. Sometimes it's a solid disk or something, then the tensions are not the same. Like in this. Anyway, there's a bunch of numbers. 0.75 times 9.8 divided by 0.05 divided by 0.2 squared plus the 0.75 plus the 2.5. Anyway, you plug in all the numbers, you get the acceleration is equal to 1.6 meters per second squared. And I can assess that right now, it's less than g. If you were to take scissors and cut T1, then M1 would just fall down with 9.8, but instead it's dragging all this stuff, so it only accelerates at 1.6. Well, that was exciting. There's one more thing on the to-do list today, and it is rotational momentum. So I told you there's an analogy to everything that was linear. There's an analogy in rotation. So remember momentum, P times V? Well, now we have the vector description of rotational motion. So we used to have V and F. Vectors V and F give you kind of a more general description. Similarly, a more general description of rotation, instead of just using omega and torque, we can use, and I guess this new concept, rotational momentum, omega vector and torque vector. In order to do that, you need, this will get us to angular momentum or rotational momentum, you need what's called the right-hand rule. So, what we say for omega, we could say clockwise or counterclockwise, but we can specify that in another way by defining a vector that's perpendicular to the plane of rotation. So we say that omega has a magnitude, which is equal to the magnitude of just omega, as we've written before, but it now has a direction. The angular velocity vector points along the axis of rotation, so perpendicular to the plane of rotation, in the direction given by the right-hand rule, which is, you take your right hand, and you curve your fingers in the direction that they normally curve, because they don't curve the other way very easily, and make that the direction that the thing is actually rotating. And then your thumb is going to point the direction of omega. So in this case, it's that way. And if I spin it around like this, the only way I can actually do it is this way, right? I have to flip my whole hand around, and now the vector is pointing down that way. Fair enough? That's called the right-hand rule. And rotational momentum, the rotational inertia, L, so we've run out of letters, so we're using L, is equal to I, which is like directionless, times omega. And this is analogous to P equals M times V. So I do have a fun little learning catalytics. This one is just moving, it's not accelerating. If your car is driving towards the right, what is the direction of the angular momentum of the wheels? The survey says. So a lot of people are getting into the page. I think that's the one that I liked. And again, you kind of have to just do it with your hand. You know the wheels are turning this way, So if you put your hand like this, that's out of the page. Doesn't work. If you put your hand like this, then that's into the page, away from you. It's that idea. And then the idea is we have something called conservation of angular momentum. Conservation of linear momentum was if there's no net external force, then an object continues with its same momentum. Conservation of angular momentum is that if there's no net external torque, then you get the same angular momentum. And so it goes like this, and this is a bit of a uncomfortable demo for me. Aziz, do you want to move the video so the... I don't know if he's there. He's still there? Okay. So this is called the Dizzy Professor experiment. And what I can do... So we have L is equal to I times omega. Thank you. So if there's no net external torque on me, then that product of I times omega has to be constant. So I can change omega by just, I guess, changing my rotation velocity. Can I change I, my rotational inertia? How do I do that? If I move the mass, some mass, these 5 kilogram masses, far from my axis of rotation, I increase my rotational momentum. So if I have some, let's give myself some external torque to get myself rotating. I have some omega value. If I decrease my rotational inertia, I have to increase my rotational or angular velocity to compensate, and I can slow down again by that. Or speed up again like that. Okay, so that's that one. And now, so next one. I'm okay. I'll get there. Okay. One last demo. I'm here. Okay. So, it comes up that in your body there are rotating protons. And these protons rotate extremely quickly. Let me go to the end of that. Very, very quickly, so that if they're going to interact with electromagnetic radiation, it has to be high energy electromagnetic radiation, basically X-rays. So that's not good. So what you can do is apply an external constant force on the protons, and they have a magnetic moment. So if you put a constant DC magnetic field on your body, then what happens is it's just like, this is a fast rotation, fast I can get it going. It's like this constant force of gravity on it. It precesses now, but at a slow rate. So there's one full rotation. Wait. There's another full rotation. This is introduced a new frequency for the wheel by applying this perpendicular constant force. And it's a much, much lower frequency than the actual spin of the wheel. Well, the same thing happens for a proton. If you've got protons in your body and you have a constant magnetic field, it causes all the protons to precess at now much lower than X-rays, way down at radio frequencies. Radio frequencies happen to be totally harmless. They pass through us all the time. But now the protons are interacting with the radio frequencies, and you can shine radio waves onto a person, find the reflected or the resonated radio waves, and you get nuclear magnetic resonance or MRIs. That's it for today, and I'll see you on Wednesday.